In electrostatics, moving a test charge within an electric field requires work. This work is stored as potential energy. Today, we will derive the mathematical expression for the electric potential at a specific distance from a central point charge. Electric potential, denoted by V, is defined as the amount of work done by an external force in bringing a unit positive test charge from infinity to a specific point in the electric field without any acceleration. To begin our derivation, consider a source charge Q at the origin. We want to find the potential at point P, located at distance r. We will first look at a small displacement dx at an intermediate distance x. According to Coulomb's law, the electrostatic force acting on the test charge at distance x is equal to k times the product of the charges divided by the square of the distance. This force pushes the test charge away. To move the charge closer, we apply an external force. The small work done dw for a small displacement dx is the dot product of force and displacement. Since they are in opposite directions, the angle is 180 degrees. Because the cosine of 180 degrees is -1, the work done is negative the force times the displacement. We substitute our expression for the electrostatic force into this work equation to prepare for integration. To find the total work done in bringing the charge from infinity to distance r, we integrate our expression for dw. Our limits of integration are from infinity, the starting point, to r, the final position. Since the electrostatic constant k and the magnitudes of the charges q and q do not change during the movement, we can move them outside the integral sign, leaving us to integrate 1 over x squared with respect to x. We now apply the limits of integration to our result. We evaluate the expression at the upper limit r and subtract the value of the expression at the lower limit, which is infinity. Mathematically, 1 divided by infinity approaches 0. This simplifies our bracketed term significantly, leaving us with only the -1 over a term to multiply with our external constants. The two negative signs cancel out, resulting in a positive value for work. The total work done to bring the test charge q to distance r is k times q, all divided by r. Finally, we return to our definition of electric potential or work per unit charge. By dividing our total work by the test charge q, the q terms cancel out, leaving the final formula, V equals kq over r. This graph illustrates that electric potential is inversely proportional to the distance r. As you move further away from the source charge, the potential drops, reaching 0 only at an infinite distance. Let's apply this. For a 2 microcoulomb charge, what is the potential at half a meter? Plugging the values into our derived formula, we calculate the potential to be 36,000 volts. Remember, electric potential is a scalar quantity, meaning it has no direction. It depends only on the source charge and the distance. Positive charges create positive potential, while negative charges create negative potential. Quick check, if we double the distance from the charge, how does the potential change? Since V is inversely proportional to R, the potential will be halved. Understanding this relationship is key to mastering electrostatics. We have successfully derived the electric potential for a point charge using calculus and Coulomb's law. This fundamental principle forms the basis for understanding more complex electrical systems. Thank you for watching. Generated by Vision Solve AI.